Right, so W is a subspace of an n-dimensional vector space V, and we're claiming that, well, W will be finite dimensional, and in fact, the dimension of W will be less than or equal to the dimension of V. Right, now, if W is the zero vector, then what's the dimension of W? It's equal to 0 by definition. And so W is finite dimensional. It's finite dimensional, and observe that the dimension in this case of W, which is 0, is going to be less than or equal to the dimension of V. All right, so we may assume that W is not only the zero vector, so it's got some other vectors in it as well. So we may assume that W has non-zero vectors. All right, so now what I'm going to do is I'm going to let S be the largest linear independent set of vectors in W. Right, so carrying on there, what happens if the number of vectors in S is bigger than n? Now, think back to the theorem, first theorem of 4.5 says that if you have an n-dimensional vector space, which is V now, and you select more than n vectors, what's going to happen to that S? That S is going to be linearly dependent. It's not going to be a basis, right? So it's going to be linearly dependent, obviously. Okay, so if S is bigger than n, then S will be linearly dependent, a contradiction. All right, so we may assume that S is definitely at most n. So S contains at most n linearly independent vectors. Okay, now what happens if S has n vectors? If S has n vectors, we know theorem 4.5.4 says that if we have a linear, if we have an n-dimensional vector space, then if you select n vectors from that n-dimensional vector space and it's linearly independent, then it's a basis. Okay, so if S is equal to n, then S is a basis. It's a basis for V, and so the span of S will be equal to W. Every vector in W will be spanned by the vectors in S. Thus, S will be a basis for W, whence the dimension of W will be equal to n, which is equal to the dimension of V. Okay? All right, so what we may assume, we may assume that S is strictly less than N. And remember that S is linearly independent. So now I just want to check that S is a basis for W. How do I check that S is a basis for W? It's already linearly independent. I just have to check that it spans W. So, right, so suppose that S is not a basis for W. What does it mean if S is not a basis for W? It means there's a vector in W that's not spanned, that's not a linear combination of the vectors in S. All right, so if we suppose this and move on to the next slide, then we get here. There exists a vector V in W such that V is not in the span of S. Now, what does the plus minus theorem tell me? It means I can add V into S and the new set will still be linearly independent. So by the plus minus theorem, S union V will be linearly independent. But what's the problem with this? We said in the beginning I selected S to be the largest linear independent set. Now if S is already as large as possible, then there's a problem, because if I add V to S, I'm creating an even larger set than S that's still linearly independent. So this is going to contradict. It's going to contradict my choice of S. So this contradicts our choice of S. And what is the choice of S? S is the largest linear independent set. All right, so this completes the proof. So that completes all right, so that's that.